let's see next one, variable partitioning scheme. The problem with internal partition is overcomes with variable partition scheme. Okay, but here how it will be done? Now we are not dividing it into different number of partitions. Okay, we are not dividing it into different number of partitions. Let us take 0 to 200 MB. Okay, the RAM size or main memory size 0 to 200 MB. We are not allocating, we are not dividing it into any fixed number of partitions. Okay, so initially it is considered as a big empty block. Okay, so the entire main memory is considered as big empty block. Okay, or whenever we a process comes to input queue, we will load it into process comes to queue, we will load it into main memory. Okay, so assume that the first process that comes to main memory is OS kernel. OS kernel is of size 40 MB. Okay, out of 200, 40 MB is given to OS kernel. Then one more process that is comes PX with 30 MB. PX with 30 MB of memory that is taken. So what is the process comes here? PX. Okay, then there is one more process that comes that is called PY. It is taking 20 MB only. It is taking 20 MB only. Then there is a process that is taking 50 MB. That is taking 50 MB. Okay, so 40, 30, 70, 90, 140. Then there is a process PB that is 20 MB, 160. Then there is one more process PC that is 30 MB. Okay, so how much? So 40, 30, 70, 90, 140, 160, 190, and there is 10 MB that is left. Okay, 10 MB 10 MB of memory that is left. And now look at here, you can see that there are no partitions. Whenever a process comes into main memory, the process will take the corresponding locations, okay, the corresponding memory segments, by leaving a final 10 MB of memory. Okay, so this particular 10 MB is left. If a process comes with less than 10 MB, we will allocate it. Okay, otherwise it will be left. But after some particular point of time, some of the processes will complete its execution. Okay, assume that py and pb both have finished its execution. Okay, py and pb both have completed its execution and left 20 MB and 20 MB holes. Okay, now this particular process left with two holes. The total main memory left with three holes, that is 20, 20, 10, 20, 20, 10, and PX, PA, PC, they are continuing their execution. Now a process PZ comes with 30 MB of requirement, main memory requirement. But what we have? We have 20 MB free here and 20 MB free here and 10 MB free here. 20 MB and 20 MB free here. Okay, so if these memory locations are free and they can allocate 30 MB, if you take the total free space, that is 50 MB, is actually greater than 30 MB process PZ. 30 MB process PZ. But due to this particular holes that are not in the same place, okay, that are not in the same place, suppose that if px finishes its execution, then we can merge this 30 plus 20 and allocate this particular thing here. Okay, otherwise if the pc is finished, okay, then we can give this particular thing to pc. Okay, right, so if there is a consecutive free memory locations, we can merge it. But here it is not consecutive free memory locations. The memory location, free memory locations, that are scattered in different places, so even though we have a 50 MB of free space even in variable partitioning scheme, here this particular fragments of memory is not internal to partition, here it is external to partition. Okay, because we are not dividing it into partitions. Because of the processes, which are previously taken this particular use this particular memory segments, and they are left because their execution is completed, that creates a hole here. Okay, that creates a hole here, memory hole. Because of that, we are getting the problem called in external fragmentation. We are getting the problem called external fragmentation. It is the amount of memory that is uh, left over within two left over, which are amount of memory that is left over, and the sum of all the memory is greater than the required process size. Still we are unable to allocate it in the variable partition scheme. That is called external fragmentation. Okay, right? So the solution for, there is a solution that is given for this particular external fragmentation, that is called compaction, or will also call defragmentation. Compaction, or will also call defragmentation, because here in this particular compaction, okay, or defragmentation, what we do is, wherever the free memory locations are there, all these free memory locations are grouped or moved to one place, and this particular processes are moved to one place. Okay, so what is mean by that? Suppose 0 to 40, then 40 to, what is this one, 70, 70 to 90, 90 to 140, and 140 to 160. Okay, now the all the memory fragments that will be come down, and all the process will move upwards with, see, the base addresses are this one, 0, 40, 70, 90, 140, 160, 190, and finally there is a leftover memory of 10 MB. Now see what will happen if we move all the process to up and all the freeholds to down. So it will make this particular thing. See, what is the size of px? 30 MB, PY, PA 50 MB, PC 30 MB. Now this particular space, okay, so the base address of PA is previously 90. Okay, now this particular base address of PA, now 90 will be changed to, okay, will be changed to 70, and PA will occupy 70 to 120. Okay, now look at PC here. Now look at PC. Now there is a free memory. These two memories will be merged. Okay, these two memories will be merged. Now there is a process PC which is having 30 MB, so which is also move to up. So this particular place, okay, this particular place will be occupied by PC. So initially, now actual the PC, what is the base address of PC? 160. Now this particular PC will be moved up, and the base address will be changed to 120. So PC, the base addresses are changed to 120, and its size is 30 MB, so it will be taken from 120 to 150, and this particular value, whatever the free MB will be there, the entire free MB will be merged, entire free memory locations will be merged. So there is total of 50 MB that is free. So out of this 50 MB, now once the compaction is finished, now we can give it to PZ with 30 MB, so 180, and makes again 20 MB whole. If any process that comes with 20 MB less than or equal to 20 MB, we will give that particular process to this particular memory segment. Okay, but the problem with compaction, the problem with compaction is that the compaction during this, the compaction is done at the runtime of the program. Okay, that is when a program execution time of the program. And when this particular, because all the base address values of process will be changed from previous addresses to new addresses, previous addresses to new addresses, and new absolute addresses will be uh, generated. Okay, but this particular compaction or defragmentation takes a lot of time, a lot of time. And the problem is, during this particular compaction, the system does not execute any other processes, because all the processes, the base addresses will be changed. Base address or relocation register addresses will be changed. So the system does not execute any programs while performing compaction or defragmentation. Okay, compaction or defragmentation. So this will reduce the performance of the system. Reduce the performance of the system. So we compaction is not efficient technique to reduce to for this particular problem. To avoid external fragmentation, the compaction is not the efficient technique. Okay, so we have seen what is internal fragmentation, we have seen what is external fragmentation. Okay, so with fixed size partitioning we will get internal partitioning fragmentation. With variable size partitioning we will get external fragmentation problem. So this contiguous memory, that means entire process will be resided at one place, will give you the high amounts of memory wastage. Okay, so that's why we'll go for non-contiguous memory allocation, where the process in the main memory can store in different parts of main memory. Okay, can be divided and stored in different parts of main memory. We'll see a topic technique called paging technique. Okay.